if I take a picture because it's sort of hard to explain.
Yeah, can you, or you share it? Is it handwritten? Or okay, if it is handwritten, take a picture and try to share that with us.
Yeah, because I think it'll be easier if I did that.
Yeah, yeah. So just for the benefit of listeners, there is a question on assignment number 2. I thought that it would interest other people. So this is the tutorial session, 8 a.m. Thursday. I'm recording it because I think that it might be interesting to other people as well. And I'm now waiting for Sandy to share his workings with us so that I can comment on it. In the meantime, you probably know that there is I posted a YouTube video yesterday on table 2, how to determine the force. So this question now, I think I'm gonna try to answer is not on that. It is what happens afterwards. Maybe you can try to explain in words, Sandy. That's also a possibility.
Oh wait, hang on, I'm nearly done. But yeah,
Okay.
basically I just use the stress to strain conversion. And then I realized that there's no stress in the X direction. So then there's only strain in the,
Now, which table you're looking at different? So you said that you were able to fill in table 2. Is that just, I just want to understand where you're at in terms of your progress.
so I've already derived the force equation. But I think that's correct. I'm not too sure if it's correct.
So are you trying to fill in table 2 now? Is that where you're at?
Yeah, table 2. That's
okay.
Good.
Yep. Now stress strain. This is Truss. So I'll try to give you while you're doing that. Can you also listen to what I'm saying when you're doing what you're doing?
Yeah, sure.
Yeah. Truss, by definition, is composed of members that cannot take bending moments. Truss members are assumed to be joined by pinned joints. So the only forces acting on truss members are axial forces, be it tension or compression. Okay, so either exclusively axial forces, which can be either tension or compression. So when you calculate the stress in a circular member subject to tension, the stress is F divided by A, area. There is no moment of inertia there. So that's the stress. Then the strain is that stress divided by the modulus of elasticity. That's strain. Does that make sense to you?
It does. So you're saying that we have to look at the stress individually of each member instead of.
Well, the first thing today is I tried to explain it. I didn't want to really do it. I can talk about it, but I don't want to write it on paper because what people do is they just try to recognize patterns and try to read the tea leaves from what I do and then just solve it on that basis. So I don't like that, but I can talk about it because to understand that, you need to have at least some reference to the lecture notes and etc. So what you do is you have the structure, you have a member. I don't know what is your member, but in the example, I think the example 1 is on BC, I think, diagonal lacing, the strain gauge. Your member will be different, definitely, because no one has BC, but it could be either one CD or DE or EF. I don't know which one. But let's talk on the example submission. There is a strain gauge on BC. Okay? So the question is, you also have the readings, strain on the BC, which is you have three different cycles. You have a P reading, Q reading, R reading. Okay. So I'll probably share my screen so that I can refer to the assignment write-up. Share. Okay, so example, submission has a strain gauge. It doesn't look like this cloud, of course, but there's a strain gauge on BC. Okay, and you have the reading of this. So there are three numbers and three different values. P, Q, and R. Okay, they are strains. So what is the stress in that member? Do you know how to calculate the stress?
The stress is just the force divided by area.
No, but you don't know the force. You know the strain.
Oh, okay.
Start from the strain. So sigma is equal to
E times
epsilon times E.
Yep.
Epsilon is the strain. E is the modulus of elasticity. Is that right?
Yes.
So you can calculate three stresses from here. So it's going to be sigma P, sigma Q, and sigma R. You with me so far?
Yes.
So from PQR readings, so this epsilon, so there are three values. Epsilon P, epsilon Q, epsilon R. Okay? Just recognize it is in microstrains. That is whatever I give you. That's 300 means 300 times 10 to the minus 6, of course. I'm sure you know that.
Yeah.
So from these numbers in your template, you can calculate the three stresses. Can you calculate this? You
yes.
can.
Yep.
Now the question is, I mean, you have to know that's just one member is not enough for you. You really have to know the force because you're given one of these joints, either D or E or F, I don't know which one. You have to do the calculations for that joint. That means you have to know the stresses or the forces in each one of these members. To be able to do that, you have to know F. In fact, that's the purpose of table 2. It asks you what F is for P cycles, for Q cycles, for R cycles, what the peak force, because those cycles given to you are like that. So there's a peak value. It is asking you what that peak value is. And the peak value of the strain is given. You can translate that to peak value of the stress. But how do you convert that to a F value? Do we agree on the question, Sandy?
Yeah, that's making sense so far.
Yeah, okay. Now, if, for example, the question was this, if I had one member, BC, like this, as I did in the YouTube video, there's this F. I don't know the value of the F is. I know that if F is equal to, let's say, F and sigma and strain, if F is equal to 1 newtons, sigma would have been 1 divided by area. Is that right?
Yes.
And strain, it was going to be 1 over AA. EA, because strain is sigma divided by E. So that would be the strain if I had a strain gauge on this. Reading the strain, epsilon. Oh, that's anyway. Let's say epsilon. So for a 1 Newton force, if F is equal to 1 Newton, that's what you get. You're with me so far in this table? Here?
Yes.
Okay. Now what we have is, we know this one. We know strain is 300 times 10 to the minus 6. How do I do that in that, and then I'll just put minus 6 here. Okay, that's the strain you're given. That's measured. That's in your template. The question is, what is F? Surely you must be able to answer that question for this one.
Yes, that makes sense, but you've chosen a value of the force. So are you saying that we should just guess what the force is?
You're not guessing it. You just you don't have. You just this is proportion. Will the value change if I had here 8? Sorry. If I had 8 newtons here, then 8 over A, that will be, that number is going to be carried all over. You know, will the, now if try to solve this. Let's say, just to make it simple, let's assume E is 1. I mean, this is not the case, but just for the sake of argument, A is 1, okay? You with me so far? Of course, E is not 1 and A is not 1.
Yeah, that makes.
So then I'll write this again, F sigma strain, and F is 1 Newton, if I assume that, and sigma becomes 1, and strain becomes 1. If I strain as 300, what will be F? This question mark. Would this, can you, what is this question mark? What is the value of F to give 300?
Oh, okay.
It's a linear system. There is direct linear proportionality.
Okay, I see what you're doing, I think.
Well, tell me what the force is in this table. What do I replace the question mark with?
300, I'm guessing.
Of course, it's 300. How do you get that? You say that this is proportional. So you say 1 over 1 is equal to question over 300.
Oh, okay. So you take the you take the ratios of the.
Isn't that obvious? Shouldn't it be like that? And does that change with whatever value you assume for F? I mean, they cancel anyway. So it is really the relation you're trying to get is the relation between this and this. So if once you get this strain for a given value of force, then you can just ask the question, okay, what will be the force to give me my own value of strain? Do you understand?
Oh, okay, yeah.
So what do you need to do? It doesn't matter what you assume for force. If you want, you assume 88.67 newtons applying, and calculate the sigma in your strain gauge member. Now, in this case, sigma is very easy to calculate. It's force divided by area, because that's this in my drawing here. That's easy. In your truss, you really have to solve the truss equation to solve for sigma in your strain gauge member. But still, you can do that. You know how to analyze trusses.
Yes, I do.
So that gives you a strain for your assumed value of F. Then for your given strain, just go in reverse, calculate the value of your force. And be aware of the signs, because it is possible that, for example, to give you your value of, if your strain gauge is here or here, I don't want to mislead. It could be in one of the members for which, for a force value, assume the force always acting in the positive direction, because unknown forces I always assume in the positive, and positive is upwards. Why in that way? Let's say for this value of F, some value pointing upwards, you calculate a strain which is negative. Let's say you calculate a strain which is, I don't know, 0.9. A negative value, that's the main thing. So what does that tell you about the direction of the force? You know your major strain is positive, but if for an upward force you get a negative strain, that means the force direction has to be in the other direction.
Yep.
Make sense? That's all there is to it. There is no I, X, X, or I, Z, Z, or whatever. Because you can analyze a truss by just using truss equations. But just joint, either by joint. The best thing is by joint. Start from H and do G and F and A, etc. Think about it.
Yeah, it's a excuse me. It's a lot simpler than I thought it would be.
Sorry? It is what?
It's a lot simpler than I thought it would be.
Yes, it is. It is simple. And really my principal learning objective in here is really to make you understand why we do put strain gauges, what's the purpose, how do we measure forces in real life, and that sort of stuff. All you need to know to make sense of the strain gauges, to get the relation between applied force, which is unknown, and the strain gauge location. And you can get that relation. This is a simple truss, so you can do it by simple truss analysis. If it were a more complex structure, then you would have to do a finite element analysis. But whatever means you use, there are good analytical techniques to calculate a strain on a given location for an applied load which is unknown. Once you get that correspondence between force and strain, then you just say that my measured strain is this. Therefore, I conclude that my applied force is this value. That's the whole purpose. if you do you have any do you have other questions, please ask, otherwise I'll stop recording on this one.
Not at the moment, but thanks for the explanation.
Does that make sense so far?
Yes, it does. I think so.
Okay, so I stop sharing and I stop recording.